Well, hello again everybody. Well, I'm sure that most of you will know that last Sunday it was Golborne. And for those of you that haven't heard about Golborne, it's actually a vintage radio and electronics equipment sale, and that's run by members of the British Vintage Wireless Society. Now, Golborne itself is just a small town in the metropolitan borough of Wigan, and that's approximately 13 miles from Manchester city centre. And the British Vintage Wireless Society also arranged several other sales of radios and vintage equipment all around the UK for the benefit of its members. Now, for anybody that isn't a member of the BVWS, I would highly recommend that if you are interested in vintage radio, that you really should go ahead and join them. Well, I've got to admit this actual radio sale was a bit of a first for me because I actually managed to sell more than I bought. And this time I did actually rent a table, and I did manage to sell quite a number of vintage related items that, well, some of them you've seen being restored on this channel. And I did actually decide to pass on the Marconi meter that you saw me rebuilding recently, and also the Lafayette communication receiver that was very deaf, and to fix that we actually replaced the first RF amplifier. And finally there was a BK Precision tube tester that, although it worked very well, cosmetically it wasn't in good condition. Now, for once I did actually end up spending very little money. I think most of these items, with the exception of this meter here, which we'll come on to, I think most of these boxes that you can see, I don't think I actually paid more than about £3 for any of them. Now, this item here, which is an RMS voltmeter, and it was made by Advanced, it didn't actually cost me anything at all, because this was given to me by my friend Paul, better known as Cody's, where he generally likes to repair things like vintage Roberts radios. So if you haven't checked out Paul's channel, you really should. There's lots of good things happening there. And I did also receive this Velleman amplifier, and this came from Andy of the Vintage Electronics channel. In fact, it's probably fair to say you couldn't swing a cat without hitting several other YouTube creators that are into vintage technology, because George Christophe was also there, and he was demonstrating his latest hairstyle.
You know when you've been tangoed.
And also fresh from his sellout US tour was Steve Pendlebury of the YouTube channel Electronics Long Stay Workshop, and he had a table at the back and he was doing his usual thing of doing a live radio repair. And of course our lineup of vintage radio and electronic stars, it wouldn't be complete without Andrew Housfer.
So what we're going to use is this special mallard hammer. Now, these were issued to radio technicians in 1967, and they were for tapping AF117s to make sure that they could actually still work and get rid of all the whiskers inside.
So I'm going to clear the bench and let's get started. So the first item that we're going to take a look at today is this capacitance box, and I can see that it's got a range between 0.05 microfarads and 28 microfarads with a rated voltage of 500 volts DC, and it's got an accuracy of plus or minus 20%. And it was manufactured by Letrokit. Now, I believe that the Letrokit name was actually a brand of the company APT Electronics Industries, and they mainly manufactured transformers for a number of manufacturers in the 40s and 50s. But they did actually commence manufacturing their own power supply, both valve and transistors, from about 1957. The company continued to expand into the manufacturing of special designs for the Ministry of Defence, and under the name Letrokit they went on to produce a number of prototype development aids for the electronics industry. In 1971 the company produced one of the first transformerless mains power supplies, but unfortunately, because most of their equipment was really quite big and heavy, chassis mounted or designed to fit into 19-inch racks, they really didn't make the crossover into modern PCB design, and unfortunately sales of Letrokit equipment gradually declined and the company eventually entered receivership in 1974. So I think it's probably fair to call this piece of equipment a capacitor substitution box. So if you're working on the design of a piece of equipment but you're not quite sure what value of capacitors to use, what you can do is you can just put this box into circuit, and then by flicking a switch you can actually introduce various values of capacitors into that circuit until you find the one that you want. So we've got a capacitance here of 28 microfarad and a maximum working voltage of 500 volts. So this box could actually store a relatively large amount of charge. And of course, if you was to actually discharge all that voltage into yourself, you could get quite a nasty electric shock, of course. So I have just noticed that, unusual for an instrument of this type, for a capacitance box that is, we do have this button here, and we press this and it's got the word discharge on it. So I'm guessing if you have charged up this capacitor bank to up to 500 volts, before you go touching the terminals, you can actually just discharge any energy stored in the capacitors by pressing the button. So we'll have to give that a try, won't we? Now, given that our capacitance box here does go up to 28 microfarads, I'm just wondering what sort of capacitors they will be in here. Of course, I would expect them to be electrolytic capacitors, because generally you need electrolytics when you have these quite high values of microfarads. But if we look at the terminals on the end here, we have got the capacitor symbol, so obviously this is where our capacitor is actually connected to, but it doesn't have an indicator of what's positive or negative. So it does make me wonder whether or not we do have electrolytic capacitors in here or not. So we're going to have to take a look at that. So we have got 3 terminals, so we've got 2 terminals here, which is what our capacitor is connected across, and then we've got another terminal here which I would probably call a guard terminal. So this is designed to be connected to an earth. Now, one thing that won't be immediately obvious on camera is actually how heavy this thing is. It really is very heavy. Now, I'm really not sure if it's so heavy because of the metal chassis, this metal construction that it's actually built from, or whether we've just got some very big heavyweight capacitors in here. I think really we need to take the lid off and have a look, because I want to see what's inside. Okay, well, it looks as though it doesn't come apart from the top, because I'm turning this screw and it's just spinning. So there must be a nut under there, so that's clearly not how you get into this thing. Maybe we take the bottom off. Let's try that. Oh, well, well, I can tell what they are. We've obviously got some capacitors in here, and I think this is the old, old paper capacitors in metal cans. So no, these possibly aren't well, they're almost certainly not electrolytics. It looks like there could be some date codes on the bottom of here, but I'm not sure I can make them out. Let's have a look. We definitely do have some date stamps here, but unfortunately I just can't make them out. It looks something like DCO or DCC, and they've got the letter 28 stamped on them. In fact, all these capacitors have got 28 stamps on them, so I'm not sure what that is. Now, from my experience, this type of metal capacitor, which is in a hermetically sealed metal can, I've actually found these to be quite reliable. I think that they're probably a mixture of kind of wax and oil material. I think we did pull some of these capacitors away in the past, so we will try putting 500 volts on it, seeing if anything explodes. That'll be interesting, won't it? I wonder if we can see a bit more if we take this side panel off. Will that allow us access into the unit? So now that we've removed the bottom and the side panel, as well as these very large metal can capacitors, which must be the high value capacitors, we've also got some of the traditional axial style capacitors. Now I can actually see they've got like a plastic jacket on them, and some of the plastic jackets just look as though, yeah, I think they may have an oily residue on them. So again, I'm guessing that these are paper capacitors. I can really see why this company went out of business, because the construction of these units really is quite complicated. Well, I can see that this thing really isn't designed to be very easy to service or get apart. It looks as though all these side panels would have to come off. And in fact, I'm not even sure how you would even get at the nuts under here to actually release the top panel, because I tried to undo one of them and the nuts were just spinning. I think that before we go ahead and put 500 volts in our capacitance box here, we will just go ahead and check the capacitance range, because I don't want to put 500 volts on it and risk any residual voltage from blowing up my DAR meter here. So let's just go through. Let's start off with the big numbers first. So let's try for 12 microfarad. So that's measuring 12.3, looks pretty good to me. Let's try 8. 8.2, pretty good. Let's try 4. Bang on, 4, nothing wrong with that. Try 2, again 2.1. And 1 microfarad, which is coming up as 1174 nanofarad. So that, again, that's about 1 microfarad, isn't it? So good enough for me. Let's try 0.5 now, so that should come up as about 500 nanofarad. Now I can see that unfortunately for our 0.5 microfarad capacitor, we're actually slightly out of our 20% tolerance because we're getting a reading of 0.62, whereas 20% of 0.5 should be 0.6, so we're 0.02 microfarads over there, so slightly out. Again, for our 0.2 microfarad capacitor, we are just slightly out of tolerance. For 0.1, we are within specification at 116 nanofarads. Here's another 0.1. Okay, again, also in specification. And finally, let's try 0.05 or 50 nanofarads. And again, for our 50 nanofarad capacitor, we are slightly out of tolerance here. It should be a maximum of 60 nanofarads, where we're actually measuring 72 here. Now I think it is actually interesting that, I think the way that this is laid out, that I suspect that all the high value capacitors, they've actually all come out on tolerance, because these big can capacitors, they're so well sealed that generally they are pretty reliable. But it does appear that these smaller capacitors here, they are actually coming up out of tolerance. So maybe if we want to in the future, we can actually change them out. I'm not actually so interested whether or not they're in tolerance or not. They're probably close enough. What I'm more interested in is whether or not these capacitors are leaky, because of course we don't want them to be getting hot and exploding when we connect 500 volts to them. So maybe we can just see how leaky they are. Now I think we might as well start testing these capacitors at their maximum working voltage, which in this case is 500 volts. So I'm going to use my insulation resistance meter here to put 500 volts onto these capacitors, and we'll just see what the leakage is. So we'll just switch on. Now at the moment we're getting an infinite reading, which is what we'd expect for a good capacitor, but we don't actually have any capacitors switched into circuit. So let's just switch in this first 50 nanofarad capacitor and see what leakage we get. Okay, so we're actually getting a leakage there of about 1.2 megohms. So immediately this capacitor is bad. We should be getting a reading of much closer to infinite. So that's not a good capacitor, unfortunately. Okay, let's try our 100 nanofarad or 0.1 microfarad. Okay, so you can see that this one is doing a lot better. We can see the capacitor's charging up, and I think the charge rate has started to slow down, but we get an indication of about 116 megohms, which is still not what I would class as being particularly good. Let's try the other 0.1. Again, a similar reading of over 100 megohms. Our 0.25 is charging up. Let's try the 0.5. Looks like our 0.5 microfarad isn't doing very well because that's got a resistance of 4 megohms. Let's try 1 microfarad. Now there is actually a limit to the maximum capacitance that you can charge up with these boxes, because they don't actually output very much. You know, of course they're not designed as power supplies. Okay, so our 1 microfarad, that's actually measuring perfectly. This is what we should see. We should actually see an actual reading of infinite on here, which is you know, that's more than 1 gigohm for this particular meter. So yeah, that's perfect. Let's try the 2 microfarad. And again, we've gone to infinity, so that's looking pretty good to me. Let's try our 8. So again, our 8 microfarad capacitor, again it's showing infinity, so that's looking pretty good to me. So again, it looks like these large can capacitors are fine. It's just the small axial ones that appear to be, well, garbage. And finally, let's try our 12 microfarad. Well, it's getting there. Okay, 1 gigohm. Now of course when you charge up these capacitors, you've got a fair amount of stored energy, and that presents quite a serious electric shock risk. So of course you want to go ahead and discharge them, so let's do that. Now of course we do actually also have this discharge button, so let's give that a test. Okay, so yeah, that seems to work as well. So that discharge button, it's definitely an awful lot better and safer than just jamming a screwdriver across the terminals. So let me put this back together and we'll move on to the next item. Now, I'm sure many of you will recognise what this is, and it also says on it it's a resistance decade box. And this particular decade resistance box has been manufactured by Fersel Laboratories Limited. Now, for those of you playing along at home, Fersel Laboratories, they were established in the 1930s in Boreham Wood, and they were best known as manufacturers of test and measurement equipment such as signal generators, spectrum analysers, resistance decade boxes like this one, and even oscilloscopes. And like many other British test equipment manufacturers, they stayed in business until around the mid-60s. 1, 2, 3, 4, 5. This particular decade resistance box is the type R600 and it has a basic accuracy of 1%. And we have 5 resistance ranges starting at 10 ohms going all the way up to 100,000 ohms. Now the actual accuracy figure here of 1% isn't really astoundingly high, but the thing that's special about this box is it's actually a high dissipation type, which means it can actually tolerate quite a lot of current flowing through it. Now a lot of decade resistance boxes, they're kind of used as standards and things in calibration, stuff like that, so you need to be really careful with. If you put slightly too much voltage across them, you're going to end up with quite a high current flowing in some cases. That will make the resistors get hot and it may burn them out, but even if it doesn't burn them out, they'll get hot and they'll go out of tolerance, whereas this box is actually designed to handle a fair amount of current. So I can see it's got that current written down here. So for the 100,000 range it can handle 7 milliamps. For the 10,000 range it can handle 24. For the 1000 ohm range it can handle 77 milliamps. For the 100 ohms it can actually tolerate 245 milliamps, and finally for the 10 ohm range it can tolerate a maximum of 777 milliamps. Now in terms of milliamps, that's not very much current, especially for these higher resistance ranges, but it's actually still quite a lot compared with what I would call a traditional decade resistance boxes. So this is one of my other decade resistance boxes, and this one is relatively low cost and it's manufactured in China. And this one's got a basic accuracy of between 0.1 and 0.5% depending on what range you're on. But certainly in terms of dissipation, these resistances in here can't tolerate very much current at all. In the case of the 100 megohm range on here, that's only a maximum of 60 microamps. So you really would have to be quite careful not to put too much voltage across some of these resistance ranges because you're going to burn them out. Whereas the high dissipation resistance box here has been specifically designed to tolerate those higher voltages and currents. And another feature of our Fersel resistance box is certainly these are the most chicken-headed knobs that I've ever seen. I am going to take our resistance box apart and we're going to give it a bit of a clean, but before we do that I thought it would be interesting just to check these resistance ranges using the Keysight 344618. And as you can see, I've actually got it set to the ohms range and I'm going to do a 4-wire measurement just to get the best accuracy we can. Now I can immediately see that even though we've actually got the resistance ranges all set to 0 here, so in theory we should have 0 ohms, we can actually see that we've got some offset here. Now when it comes to resistance decade boxes, even ones that do have a 0 ohm setting like this, you can't actually achieve 0 ohms because that would mean that the switches and all the wiring inside would have to have 0 resistance. Now that isn't actually possible. You can actually get switches that have got very low resistance, but you can't actually get a switch that's got 0 resistance. And the same with the internal wiring within our resistance box. We've got lengths of wire inside that, and inevitably those lengths of wire will have a small amount of resistance. Let's try a 10 ohms range first, so we're going to set 10 ohms now. And we can actually see that for 10 ohms, again, this resistance box, it's actually slightly outside its 1% accuracy figure because we're getting 10.4 ohms, whereas a 0.1 accuracy would be 10.1, wouldn't it? So we are slightly above that. Let's go to 20 ohms. Again, slightly out, but we can actually see that the offset seems fairly constant. It really is pretty constant, that offset, around half an ohm. I guess that another thing is that this resistance box probably hasn't been used for 20 years, and it is actually pretty good practice before using one of these instruments is you should actually give the switches a bit of a flick because that just gives it the opportunity to wipe the contacts and clean themselves. And I'm actually glad I did that. So you can see that just by giving all these switches a bit of a flick round, we've actually reduced it by nearly half an ohm. So yeah, these switch contacts were obviously quite dirty, so they might even respond to a little bit of very carefully placed switch cleaner. Let's try the 100 ohms range. And for the 100 ohms range, I can see that we are actually in tolerance for pretty much all the settings. Okay, let's move on to the 1000 ohms now. And for 1000 ohms we are within our 1%. Let's try 2000. And all the way up to 10,000. Let's move to the 10,000 ohm decades. So here's 10,000. Very slightly out at 198. We really wanted 199, but I'm not going to complain. Yep, that all looks pretty good to me. And finally, let's move on to the 100,000 ohm decades. And again, that looks pretty good to me with a maximum reading of 1 megohm. Now, if you're going to buy a resistance box, it is definitely worth just running it through all the different resistance settings and trying all the switches, because it really is very common to find that some of the resistances inside these can be burnt out. But luckily, this one looks good. Let's open it up and have a look inside. Now, I'm not sure how this comes apart. I suspect if we undo these end caps, it might just all slide out. Got a terrible feeling this might just collapse any second like a house of cards. Oops, it's all very wibbly wobbly now. Can we get it apart? We should be able to. So taking a look inside our decade resistance box, we can see that it isn't particularly exciting. It really is just a stack of wafer switches, and between those wafer switches we've got some power resistors, and it looks as though these power resistors are made by the company. I think that says Zenith on them, and it's got the wattage as well as the resistance value actually written on the side of them. And you can see that these resistors are actually quite a nice green colour, and they're kind of made from a ceramic stroke porcelain material. Well, I think they actually call this design of resistor, I think they would call this vitreous enamel. I think that's what they used to call these. You can see at one end we've got a little hand label that's been put on there as part of the QA, the inspection process. Fortunately can't quite make out the name, but obviously it was checked. Just taking a close look at this guard connection, which allows the resistance box to be earthed, we can actually see that it's actually hand scraped to make a good connection. So we seem to have like this blue protective paint material on the aluminium. Quite often you get that on bare sheets of aluminium, but somebody's actually taken a file and they've actually filed that off. So I think it's interesting to see that, you know, these types of old equipment, every one of these was put together by somebody in a workshop. And taking a close look at the switches, they really aren't anything very exciting. They're just a typical wafer switch that you might find for controlling the waveband on a vintage radio, something like that. And there's certainly nothing special about the actual way the contacts are made here. This is, you know, pretty standard stuff. So this box itself really wasn't designed to be super high accuracy. Taking another look at the resistances, we can see that all the resistance ranges actually use 9 watt resistors, apart from the 100,000 decade range, because this one's using 12 watt resistors. So after 60 or 70 years, as you can see, everything really is quite dirty and dusty inside. So I'm just going to brush off the worst of the dirt and the dust, and then I am going to just spray some switch cleaner onto the contacts. Now, for certain precision decade boxes, you'd have to be very careful with things like switch cleaner, because if you're not careful, the actual oily residue can actually soak into the wafers here, and it can actually affect the readings. But this one isn't designed to be ultimately a high precision unit, so I think it will benefit from just a little bit of switch cleaner on, and maybe we can see if we've done anything to improve that about half ohm of resistance that we had. I can also see at the bottom of the switches here we've got a ball bearing indent system, which is for indexing the pointer on the front so that they actually go with a click when you select the resistance ranges. These would have had a little bit of grease on them back in the day, so we'll go ahead and we'll put a bit of lube on there as well. Unfortunately, it is very difficult to control these cans of deoxit. It does just end up going everywhere, doesn't it? And of course, not forgetting to lubricate my balls. I'm going to finish screwing this back together and we'll give it another quick test just to see if cleaning those switches has reduced the resistance anymore. So I've gone ahead and I've set the decade resistance box to its 0 ohms setting again, and as you can see we've actually got quite a big improvement on the resistance level. So previously the standing resistance was about 0.5 ohms, maybe slightly lower, but now it's 0.037, so we're actually at a decade, we're an order of magnitude lower just from cleaning the switches. Well, the next thing I've got for you on the bench today is a Weston standard cell, and it was manufactured by the Muirhead Company Limited probably between the 1950s and 60s. Now if you've got any interest at all in precision measurement, no doubt you've heard of the Muirhead Company. In fact, they actually did manufacture a whole range of different equipment for use in laboratories, and most of that was electrical equipment, but they did also do some mechanical equipment, and they even made a range of medical equipment as well. So Muirhead was actually founded by Alexander Muirhead back in 1894, and that was in Beckenham, Kent. So this device is what's known as a Weston standard cell, and it was actually invented by Edward Weston in 1893. So Weston cells like this were actually accepted as the international EMF standard back in 1911, and they did remain as the international standard from 1911 all the way till the 1990s, when they were actually replaced by the Jovison voltage standard. Now I don't think this type of standard is really very useful today because there is a lot of relatively low cost voltage standards which are just as good, if not better than this one, but it certainly is interesting. So although these are often described as being a 1 volt standard, they don't actually output 1 volt. The actual output voltage from a Weston cell is about 1.018 volts. However, I've noticed that at some point in the past somebody's actually fixed a label on this one indicating the output from this is 1.019 volts. And I have also just noticed that somebody's actually scribed a voltage measurement back in May 1982, and they've actually got it recorded as 1.085 volts. But again, we don't know what they actually used to make that measurement, so I think it might be interesting to actually just check what it is today. To check our Weston cell, I'm going to use this Keysight 344661A, which is a 6.5 digit multimeter, so it is relatively high precision and accurate. So let's go ahead and plug in, and remember we're looking for 1.018 volts. But we are actually reading just under that at 1.01162 volts. Now I've got to admit I'm not exactly sure how old our Weston cell is. I suspect it's probably late 50s or early 60s, so of course 60 years later it's maybe not surprising that it is slightly out of specification. Now I've actually got another Weston cell just for comparison, and I think that this one is probably a similar age to the one we've got here, but let's give this one a try because it might not have had such a hard life. And in fact this Weston cell here is absolutely spot on, 1.018 volts. So again, this is probably also about 60 years, so it just shows how stable these are as a calibration standard. Now this type of Weston cells were used back in the day to do things like calibrate sensitive voltmeters, but you would also find them quite frequently built inside pieces of test equipment. Any piece of test equipment that again needed a very stable and accurate voltage reference, they tended to build these things into them. Now if any of you are wondering what I actually paid for this, I actually paid a grand total of £1, and to be quite honest I bought it for two reasons. One, I actually thought that it was just quite interesting and I wanted to show it to you, but the other reason I bought it is because I actually thought that this was quite a useful box, and at the price of £1 it was really just too cheap to be missed. Now at the heart of our Weston cell there's actually nothing really much more complicated than a battery, but certainly the output voltage from that battery is extremely stable. I'm sure that you'll agree that internally our Weston cell here, it's actually quite interesting. It's not so much a piece of electrical equipment as something you might find in a chemistry lab. And I can actually see that we've got what appears to be some crystals or some liquid that's actually sloshing around inside these test tubes. And just reading the label, it says Muirhead, Weston Standard Cell, EMF 1.0159 volts, serial number 7202, and it's actually got the date on, which I think is the most interesting. That's what I wanted to see. So the date is 13th of the 9th 1957. So yeah, it really is pretty much 60 years old, isn't it? No doubt the chemicals that are contained within these two test tubes are enough to give a tree hugger a heart attack, because it's actually an amalgam of cadmium and mercury. So really, everything a growing boy needs. And the next item on the bench is another decade capacitance box. Now unfortunately I haven't been able to find out very much information about Winston Electronics. There's actually several companies that have the name Winston Electronics, but I believe that this unit was probably manufactured by Winston Electronics, and they were of Shepperton, Middlesex. And it appears that they were another manufacturer of various pieces of electronic test gear. And amongst the equipment that was manufactured by Winston Electronics, it included things like electronic flash guns in around 1955, and they also made temperature controllers. And it appears that they also had a number of military contracts, and they used to manufacture and also recondition radar equipment. However, we can tell by this very oldie-worldy English font that this capacitance box was clearly designed to be used by Betty's Tea Shop. Now, I have already given our decade capacitance box a bit of a test, but unfortunately I can in fact promise you that any of the measurements here, they're actually purely coincidental to what might be set on the dial. So for example, our set capacitance of 0.4 microfarad actually indicates 0.8 on the DR meter, whereas the 0.5 does actually measure approximately correctly. 0.7 is also seriously out, as is 0.8, as is 0.9, as is the 1 microfarad setting. So really we can only assume that the capacitors inside here have really seen better days. Let's take a look. Well, quite clearly more people have been inside this than a Barnsley girl, and I think you really would be quite hard pressed to find such a bunch of crap capacitors. So starting from the left hand side, we've got some mica capacitors which have been crudely bodged together. Then we've got a really horrible waxy thing with a 750 volt working voltage. Then we've got another mica. Then we've got another TCC capacitors. These were fairly crap even when new. It looks like maybe these are, would they be polyester? Much more modern capacitors. Then we've got some kind of metallized Jubilee capacitor, but effectively probably another paper capacitor. Then some more polys. Then it looks like maybe we've got an electrolytic made by ITT. And then we've got what looks like another TCC branded capacitor, and it looks very similar to the metal pack capacitor that we found in the electronic capacitance box. So although it does have a band on it, I suspect that this is another paper oil capacitor rather than an electrolytic. And then we've got what I think is a Weimer capacitor, and finally we've got another crappy British made wax capacitor which says type 743. Oh, and it is in fact another TCC capacitor. So in the future we will go ahead and we'll replace all these capacitors, but that's going to be a repair for another day. Well, to finish off with today, we've got a pair of dirty German girls, and these two are absolutely filthy. So what we've got is a fine pair of decade inductance boxes. So this one goes up in 1 millihenry steps, and the second one here goes up in 10 millihenry steps. So let's give them a quick test. And starting at 1 millihenry, 1016 microhenries, 2 millihenry, 3 millihenry, 9 millihenry, 10 millihenry, and this one goes all the way to 11. And unsurprisingly, it's 11 millihenry. So of course I'm not going to let her beautiful sister go without. 20. And finally 110 millihenries. Of course we wouldn't expect anything less from Grundig, German engineering at its best. Well, I can't wait to get inside her. Let's take a look. Well, I'm afraid with the exception of this very nicely engineered switch, there isn't actually very much to see. So it would appear that the ident for the clicky switch is really quite nicely engineered. Unfortunately you can't see it on camera, but we've got a star wheel here, and underneath the star wheel there's actually a cam which is spring loaded, so every time you click the switch the cam just moves over one position. So it gives a very smooth and a very positive switch action. The switch contacts themselves are nicely engineered, but certainly nothing to write home about. They are just what I would call a traditional wafer switch, although the contact fingers themselves do look quite robust in nature. Now it would appear that our 11 inductance values are actually made up of a series and parallel combination of these 4 inductors here, and each of the 4 inductors is wound on a ferrite bobbin. All in all, a very high standard of construction, which of course we'd come to expect from German engineering. This inductance box is the red unit, so this is a 10 millihenry unit. Now I can actually see we've got some numbers printed on the table, but I've got to admit, I'm not quite sure what those numbers refer to. We've also got a graph here, and again I'm not sure really what this graph is indicating because, well, it doesn't seem to have any units on it, and I don't speak German. It looks like one of them is in hertz and the other one is in Gut. What's Gut? Frequency? Don't know. Suppose I should Google translate that. Can also see that we've actually got a 2% specification for the accuracy of the unit. And like most men, I do appreciate a nice pair. Well, unfortunately today, as you can see, we didn't manage to get through all our Golborne purchases, and we do still have the advanced RMS meter and the Quark process multimeter to look at. But if you do want to take a close look at these items, please leave it in the comments. But for today, that'll do. And until next time, bye bye for now.